Hey everybody, it's Mr. N, and we are going to be talking about maximum and minimum values. Now, you first started dealing with maximum and minimum values of curves probably in Algebra 2, or maybe before that, in Algebra 1, where you had to find the peak or the maximum value of a parabola. You found the vertex, and that determined whether it was the maximum or the minimum based on if it was concave up or concave down. You were able to do it with your calculators in methods that you learned, or by finding your x-intercepts and determining where the vertex is. But there were multiple ways that you did it. But in any case, here we're going to talk about a global maximum. So if we have an absolute maximum, that's an absolute maximum. It's the absolute highest value we can get. This is called a global maximum as well. If we have an absolute minimum, it's a global minimum. But let's determine what the absolute part tells us. A function has an absolute max at C if f of c is greater than or equal to f of x for all x in D where D is a domain of f. F of c is called the maximum value of f on D. So let me explain to you how this differs than a regular maximum, or a relative, or a local. That's what we really call them, and I'll get into that in a second. But suppose I had some grid here, okay, and I had a curve on this, and the curve, say, started like right here, went down, went up, went back down, and say it continued in a downward trend. Well, we know that this right here is a maximum. If I find what it relates to over here on the axes, okay, suppose this is at 5, and then this right here, though, on the axes is at 5.5. Okay, I'm just coming up with numbers here, just random numbers. Notice that this 5.5, and let's enlarge it a little bit if I can. We'll bring this in. Notice that over here, when I say I've got the value of 5, but then this value right here is higher, and I will put it right there so you guys can see a little bit. That value right at that point is bigger. That means that this is a maximum value because it's the top of this curve, but it is not the absolute. The absolute would be this one that I called 5.5. That would be the absolute maximum. That's the absolute highest point on this graph in whatever domain we're looking for. So sometimes it may not have an absolute because it could go on to infinity. So let's bring this back over here. And an absolute minimum, again, if I use this curve, here's a minimum value, but the absolute minimum, suppose my domain here was from, we'll say that this is at 0, and we'll say that this is at 10. So there's my domain. Well, my absolute minimum would not be here, which is maybe like at 3. We'll just call that 3 hypothetically. Okay, my absolute minimum would be over here at 10. That is the absolute lowest point on the graph. So that's what absolute means, and often we call these globals. So what tells us something important is whenever we're testing for maximums and minimums, we always have to check the endpoints, because the endpoint of the domain is what I'm saying, because it could be higher or lower than any of these relatives that I find. So maximums and minimums are called extreme values. So other extreme values that are not absolute are called local. We can also call these relative. You'll often see this word relative max or relative min. My pen's giving me a hard time. Relative max and relative mins as opposed to local. If we're looking here again at this example, here this f of d is an absolute maximum because that's the absolute highest point I have on this curve, whereas f of a right here is an absolute minimum. That's the absolute lowest point I have on the curve, and this would be a local minimum. All right, let's slide this up. So we can come up with this definition now that a function has a local max or relative max at C if f of C is greater than or equal to f of x, when x is near C, and it tells us that f of C is greater than f of x for all x, I should say x, in an open interval containing C. F has a local minimum or relative minimum at C if f of C is less than or equal to f of x when x is near C. So again, here, just so we can correct it, this should say for all x. I need to put an x right in that spot. Okay, so that gives us this next thing, which we call the extreme value theorem. And let's go ahead and bring this in a little bit so we could see all parts of this in the notes. And here we have, if f is continuous on some closed interval from a to b. Now notice the closed interval. This tells me that you're looking at the endpoints. Then f attains an absolute maximum value, f of c, and an absolute minimum value of d at some numbers c and d in AB. In other words, if the interval is closed, because now I can equal the endpoints, right? So if the interval is closed, which means I will have a value here. It's closed. It's closed. This point, it is not an open circle there. I have to include a value here at these endpoints. Okay? So as long as the interval is closed, I will have an absolute maximum or absolute minimum. And that's what the extreme value is telling me. As long as the interval is closed, you will have some sort of absolute max and absolute minimum. Whether it occurs in the curve itself or it occurs at the endpoints, you will have one. So that means if it's continuous on AB, it will have an absolute maximum, absolute minimum. So where is the absolute maximum or absolute minimum on each of these examples? On this first one, well, there is the absolute max, okay? Right here. We'll call this one the absolute maximum. And I will just say that this point right here, I'll say that this is lower on this side, so we'll just say that that's the absolute minimum. My pen is having a hard time today with some things. So, okay, so we'll just say that this is lower than this one. Okay, over here. Well, where's the absolute maximum? Okay, again, I should have drawn this a little bit better. I didn't. So excuse me on that. Let's erase this. What I'm going to do is I'm going to extend this up. I'm going to extend this curve up a little bit so it's nice and clear what we're looking at. Okay, let's see if I have to fix any of the other ones. No, the other ones look good. Okay, so over here, where is the absolute maximum? The absolute maximum occurs right here. This is going to be our absolute maximum. Okay, where will our absolute minimum occur? This point right here is going to be the absolute minimum value. Okay, where on the next one is our absolute maximum or minimum? I'll give you a second to think about that. Would this be the absolute minimum right here and this is the absolute maximum? No, none, no, none, no absolute, no absolutes. Why? What does it say it has to be? Continuous. Okay, this is not, this is absolute, not continuous. Okay, over here, what's wrong with this next one? Where's the absolute maximum? It's not a closed interval. Not a closed interval. Okay, because this continues upward, this continues this way. So it's not a closed interval. No absolute max or min. Okay, so you have to take a look and you have to see if they are on a, if it's continuous and a closed interval to be able to get an absolute maximum or absolute minimum. So here we go on this page. We're taking a look at Fermat's theorem. All right, Fermat was an amazing mathematician. And just to give you a quick background on Fermat, before I talk about this theorem, Fermat had this other theorem which he called, which they called Fermat's last theorem. Okay, and he was, you can call him Fermat, but that's how a lot of people pronounce his name. But anyway, he had said that if you have You guys are used to seeing this, right? If you say a squared plus b squared, you guys all know this one. It's equal to c squared, right? Well, you can come up with combinations. And Fermat said that, look, if you have a to the n plus b to the n equals c to the n. Sometimes we see it as x to the n plus y to the n equals z to the n. Sometimes we'll see it instead of ABC, we'll see the XYZ version of it. Well, Fermat said that, okay, if you've got a positive integer greater than 2, you cannot find values for A, B, and C that will work. And he proved it. Where did he prove it? On his deathbed. He said, I've proven it, here, and I know it, and he died. And this was, I believe, in 1637. And it didn't take, people couldn't prove it. They said he proved it, but he didn't write it down. There were scribble marks. They were trying to decipher what he had said and what he wrote down, and they couldn't do it. Because often he proved things and he put them in corners of books and things like that. But nobody knew how to prove it. Nobody could prove it, even though he said he did. And it took until 1995, I believe, and it was Andrew Wiles from St. Andrews that actually proved it. There was a contest. $1 million was given to anybody who could prove this. Well, he proved it. And he had to write books on developing different maths to prove it. So quite a big story there, quite an interesting story, but hey, it was $1 million prize at one point. But anyway, Fermat had a lot of theorems. And another one that he had that we're going to be using a lot, and it develops something else that we're going to talk about soon, is this one right here. And it says, if f has a local maximum or minimum at c, and he's saying local, and if f prime of c exists, then f prime of c is 0. Wait a minute, prime? That's the derivative. We've been taking the derivative. That means if f prime of z exists, then f prime of z. So that means if I find a derivative that equals 0, if I find a horizontal tangent, that's what this is saying, a derivative that equals 0. This is a horizontal tangent. If I find some horizontal tangent that equals, right, because a horizontal tangent will equal 0, then that's going to give me a local maximum or minimum. Whoa, pretty cool. And this is very important because Fermat is saying that if f prime of c exists, we can set it equal to 0 and find any local or maximum minimums that we have. That's astonishing. So look, I don't have to graph it. I could do all this without graphing. So look at this example. All right, this is cool. F prime of x equals x squared plus 1. All right, or f of x, sorry. F of x equals x squared plus 1. Take the derivative. F prime of x. Fermat saying, all right, cool. Set this equal to 0. So you get 0. So that means we have a maximum, a local maximum or local minimum at 0 comma f of x. When I plug in 0, I get 1, right? So we found right here. This is really cool. We found, and in this case, look, you know that this is going to be a parabola that opens up. So you found a minimum, and more specifically, you found a relative. Oops, my pen is just giving me a hard time today. You found a relative minimum at this point, 0 comma 1. All right, let's take a look at another example. Wait, be careful, Fermat's theorem doesn't. What? You mean it doesn't always work? Okay, let's take a look at this example. Suppose you had x to the third. So f prime of x equals 3x squared. Okay, I set this equal to 0. I get 0, 0. Cool. That's a maximum or minimum. Wait a minute. Wait a minute here. Let's take a look at this graph. Okay, if I graph x to the third, you all know this. You should at least. This graph looks like this. At 0, 0, right here, that is not a maximum nor a minimum. It's neither. So, wait a minute. It doesn't always work. So that means the converse of Fermat's theorem is also false. But nonetheless, Fermat's theorem is super duper important because it gives us a starting point. It gives us a point where, hey, look here, set it equal to 0, and you can tell and determine that it may have a relative maximum or minimum there. So what it does is it gives us right here, which is what I just talked about, a starting point. And we're going to call that starting point a critical number. Where we start looking for those, when we set it equal to 0, get the answer, these are going to be our critical numbers. It's where to look for them. How do we know if they're max or minimums? We have to test them. We'll talk about how to test them in a little bit. But it gives us this thing called a critical number. Let's highlight this. This is a critical number. So what is a critical number? Well, it gives us a place that is a possible maximum or minimum. So the critical number of a function f is a number c in the domain such that it is either f prime c equals 0, or here's the next one we have to take a look at. It's either 0, oops, I don't know why it did that, wrong choice. It's either 0, and now take a look, here's a second important part, or does not exist. Okay, so not only are we setting it equal to 0, we're setting it equal to get any spot where it does not exist. We want something called the critical point or the critical number where the derivative is 0 or the derivative does not exist, and that's where we start looking for maximums or minimums. So let's do this first example where we are going to look for critical numbers. Find the critical numbers for this. Well, how do we find critical numbers? The process is, oops, I keep picking the wrong thing with my tool here, and we are going to take the derivative of this and set it equal to 0. Okay, so f prime of x will be 3x squared minus 12x plus the 9, right? And that's derivative of constant 0. Now set it equal to 0. And we're going to go ahead and solve this. And I can solve this by taking out a 3, and I'm left with x squared. Again, I'm going to have to change out to the other pen here soon. X squared minus 4x, okay, plus 3 equals 0. And take this one step further. This is going to be x plus 3, x plus 1, so x plus 3 when I factor it, times x plus 1, and this equals 0. And so then I get 2 points here. X equals negative 3 and negative 1, and these are my critical numbers that I solved for. Okay, let's do the second one. So here we take the derivative, and let's move this up a little bit. And over here, we're going to have f prime of x, and this is going to be, well, we're going to need the product rule on this one, and I'm going to go ahead and say the first, which is x to the 3/5 times the derivative of the second, which is going to be negative 1, plus the second times the derivative of the first, which will be 3/5 x to the negative 2/5. All right, so now I can clean this up a little bit when I set this equal to 0. And here I'm just going to rewrite this like this. I'm going to say f prime of x. This is going to be negative x to the 3/5. And then this will be plus, and then we'll say this is 3 times the 4 minus x all over 5, and this will be x to the 3/5 like that. I'll just go ahead and write it like that. So I'm going to set this equal to 0, and I'm going to solve it. All right, this one's a little bit harder to solve, so let me do a couple things first. So over here, I'm going to find a common denominator, and that common denominator will be 5x to the 2/5. Sorry, this should have been 2/5 right there, right? 2/5. 5x to the 2/5 is the common denominator. And over here, as a numerator, I'll have negative x to the 3/5 times, I'm going to need this 5x to the 2/5. Okay, plus over here, I will end up with, I've got this 3 and just this 4 minus x, which will just stay like that. All of this equals 0, of course.
Okay, and then let's see what we can do with this. Here I will get, this will be when I combine these, right? And then distribute and clean. Well, I don't need to distribute. That's all I got to do is combine those, and I'll actually end up with negative 5x. Wow, that kind of actually worked out, because when I get 3/5 and 2/5, I'll get 5/5. So yeah, it worked out. 4 minus x all over here, 5x to the 2/5 equals 0. So really, I want to know where it equals 0 or undefined. And at this point, we know that I can take this top part, this negative 5x, and this will be plus 12 minus 3x, set this equal to 0, and I will get x equals 3 over 2. And undefined, when x equals 0, this is when it's undefined. So where are my critical points? Well, my critical points are at x equals 3/2, where it equals 0, and x equals 0, where it's undefined. So again, remember, you're looking for f of prime of c equals 0, or f prime of c does not exist where it's undefined over there. Okay, so this closed interval method is what we're going to talk about next. And on the closed interval method, to find an absolute maximum or absolute minimum, okay, find all the critical numbers. So this is how we find critical numbers. Find f of a and f of b. This is the endpoint. So what this means is you are going to look at the end points. Okay? And take the largest of f of a, f of b, or those critical numbers, whichever is the maximum or the minimum of those three, and that's how you find the absolutes. So let's take a look at a few more examples. Over here it says sketch a graph of f on 0 to 6 that has an absolute maximum here, absolute minimum there, and a local at 5. Okay, so let's just do this on the side over here. I've got my axes, and I've got an absolute, and now answers can vary on this a little bit, but I do have an absolute maximum at 3. 1, 2, 3. I'm just going to put this way up high. Okay, I have an absolute minimum at x equals 0. So I'll just put it right here. This is at 0. And I know that I won't go below that point. I won't go above that point. And I have a local minimum at 5. 1, 2, 3, 4, 5. So a local minimum, so that's got to be down here somewhere. And then here's 6. So we'll put 6 maybe like right there. It doesn't really matter. So basically what I'm sketching is this curve that goes up, hits a maximum absolute right there, and then comes back here. This is a local right there at 5, and it's on the interval from 0 to 6, and it has an absolute maximum at 3. There's the highest point of the graph, and it has an absolute minimum at 0. This is the lowest part of the graph right here. All right, looking at the next one, I'll graph it right here. We have on the interval from 0 to 6, we'll say there's 0, there's 6. We have an absolute minimum at 4. So we have at 4 right here, we have an absolute minimum value. I'll put it down here this time. It doesn't matter. And then we've got an absolute maximum at 2. I'll put that way up there. So it doesn't matter where it starts. It could start here. It could start down here, but it can't go below this point, and it can't go above this point, right? Because these are absolutes. So we'll just start it here. It'll go up and then come down. This is the absolute, and maybe comes back up to around there. Again, answers can vary, but the key is you can't go higher than this point, and you can't go lower than this point on this interval. Just like here, you can't go higher than this point, you can't go lower than this point, and here was a relative minimum at 5. All right, find all the critical values. Here's where I suggest pausing this and doing this on your own, and then we'll check these answers. Okay, so pause it, do the problems, and come back and watch me do them. All right, so for this first one, over here, I'm going to take the derivative. Again, critical numbers, I take the derivative, I set it equal to 0, so f prime of x, I will get 3x squared minus 3. I set this equal to 0. And I'm going to change this pen size real quick. And Over here, I could take a 3 out. I'm left with x minus 1 equals 0. So x equals, this should say x squared minus 1 equals 0. So x equals plus or minus 1. Sorry, I had to think about that for a sec. So x equals plus or minus 1 are your critical points for this one. All right, over here, you could, I skipped a step. You obviously knew that this was x plus 1, x minus 1 when I factored it there. Okay, on this next one, again, we're going to take the derivative. We're going to set it equal to 0. Let's do a different color here. So this is f prime of x. This becomes, when I take the derivative, I'm going to get 15 thirds, which is 5. Let's erase that and just put a 5 there. It'll be a lot easier to work with. So we'll put a 5, and this will be x to the 2 thirds minus 15 times 2 thirds. This would be 10 x to the negative 1 third right there. And of course, I'm setting this equal to 0 to get the critical points. Now, you're tempted to bring this over to there and solve, but do not do that, okay? Do not do that. Always factor, because if you do that, you're going to leave out a variable, or a possible solution, I should say. So always factor it. So over here, I'll take a 5, and I could take an x to the negative 1 third out. You always want to take, it's easier if you take it with, on this one, with that lowest value, because look, if I take out a negative 1 third, over here, this is gone. That'll just be a 2 on that side, minus, and look, if I take this out of here, remember you're adding these up, I'll get x to the first power, okay? Because that'll just end up being 3 over 3. So this equals 0, because I'm taking it out, right? So, and in any case, that's what will end up being there. So I get over here x equals 0 and x equals 2 as the two solutions. And these are your critical points. And why did I pick 0? Well, 0 would obviously make it equal 0, but more specifically, 0 actually makes this undefined. Okay, taking a look at the next one over here, y equals cosine x. Well, y prime equals negative sine x. I set this equal to 0. And look, this negative sine x goes down, comes up, goes like this. So that means x is going to be k times pi, because that's where it'll be those 0 values. This is at pi, this is at 2 pi, every multiple of pi, so we say k times pi. If I specified on the interval, then you would just put the ones that would work on that interval. All right, moving on. We've got 2 more problems here that we're going to do. This one, number 3, find the absolutes this time. We're looking to do the absolutes. Okay, so we want the absolute maximum, absolute minimum on each, but only in this interval. All right, so what do I do to get absolutes? Well, step 1 is I need to find the critical values, and then I need to find f of a and f of b, and then test all of them. How do I test them? You just put them back into the original equation. All right, over here. So f prime of x, this becomes 6x squared minus 6. I set this equal to 0. I could take a 6 out. I'm left with x squared minus 1 equals 0. So x equals plus or minus 1. So I need to test x equals 1, negative 1, and the endpoints. So I need f of 1. I need f of negative 1. I need f of 0, and I need f of 4, because these are the endpoints. So I need to test all that. And how do I test it? Again, I just said, put it back into the original equation. All right, so we're going to put f of 0, and I'll do that one first, back into the original equation. That comes out to be 7. I'll put f of 4 into my original equation, put 4 in right here, 4 cubed times 2 minus 6 times 4 plus 7. I'll save you the hassle, and I will tell you that that's going to come out to be 111. Okay, then I'm going to find f of negative 1, put in, and positive 1. Okay, so f of 1, put this in, and I'll get 1 right here, which will be 2 minus 6 plus 7, so that gives me 3. And then when I do f of negative 1, I'll get 11. So, which is the absolute maximum? Which is the absolute minimum? Over here, I take a look at this. The smallest value occurred at f of 1, and the largest value occurred at f of 4. So I can classify these as my absolutes. So this is your, oops, I always do that and pick the wrong tool. Okay, so this is your absolute minimum, and this is your absolute maximum. So the absolute minimum occurred at x equals 1. The absolute maximum occurred at x equals 4. Okay, and that's how I went through and did that problem. Okay, let's take a look at the next one. For this one, let's see what we got here. We've got f of x is that, so let's take the derivative first, and I will get 4x cubed minus 4x plus 0, right? And then I set it equal to 0. So first we find the critical points, and this was all outlined in those steps that we said. And then the second thing, you need to find f of a and f of b, which are the endpoints. And then step 3 is you need to test them all. All right, over here I could take a 4 and an x out. I'm left with x squared minus 1 again. All right, so this gives me x equals 0 plus or minus 1. And then my endpoints are those. So I need to test f of 0, f of negative 1, f of 1, f of negative 2, and f of 3. And how do I test them? I put them back into my original equation. And to save you time, I've already done this for you. Let's find out what all these values will be. F of 0 comes out to be 10, of course. F of negative 1 comes out to be 9. F of positive 1 also comes out to be 9. F of negative 2 comes out to be 18. And f of 3 comes out to be 73. So this right here gives me my absolute maximum. And look, my absolute minimum occurs at 2 values. So yeah, you can have 2 values for the absolute because, or you can have multiple, I should say, because that's where they occur in this case. So the absolute maximum is at x equals 3, and the absolute minimum is at x equals plus or minus 1. Now that's where the absolute maximum and that's where the absolute minimums occur, but that's not the value. So there's a difference, and I will specify this and I will be specific. So listen to what I'm about to tell you right now so we avoid any confusion. If I say where does the absolute max or min occur, this is the x value. So when I say where, it's the x value. When I say what is it, then you're going to give me the y value, right? So this would be the f of x value. Okay, so over here, for this problem, where did it occur? At, oops, I can't do an at symbol anymore, it appears. Okay, this occurred at x equals 3, x equals plus or minus 1. This was the absolute maximum. This was the absolute minimum. And what were the values? What is, so I could say, what is the absolute maximum? Absolute minimum. What is it? Well, in this case, the absolute maximum was 73. The absolute minimum was 9. So where did it occur? At x equals 3. At x equals plus or minus 1. What was it? What was the value? 73 and 9. So always be careful whether they're asking you where does it occur and what is the value. All right, so hopefully that helped. We'll do a couple more examples in class. So thanks for watching. Hit that like and subscribe button. I know this was a long one. Hopefully you got it though, but hit that like and subscribe button, and I'll see you guys in the next video.